Hello friends, I welcome you in lecture number 8 on complex differentiation. In this lecture we are going to discuss differentiability of complex function using Cauchy Riemann equations in polar form. We are familiar with the Cartesian form of Cauchy Riemann equations. We know that if our function is written in this form, that is u as a function of x and y plus I times v is another function of x and y, then Cauchy Riemann equations are given by del u by del x equal to del v by del y and del u by del y equal to minus del v by del x. Here x and y are Cartesian coordinates, therefore this is called Cartesian form of Cauchy Riemann equations. And we know that if these two equations are satisfied at some point, say z equal to ordered pair xy, and if these first order partial derivatives are continuous at point z equal to ordered pair xy, then this function is differentiable at z equal to xy. Now here we are using Cartesian form of complex variable z equal to x plus iy. But suppose instead of Cartesian form we use the polar form of complex variable x plus iy, which is r times cos theta plus I sin theta. Then this u and v will be functions of polar coordinates r and theta. So in that case we will have Cauchy Riemann equations in polar form. So sometimes if we are not comfortable with Cartesian coordinates, we can use the polar form of complex variable in a given complex function, and we can write u and v, that is real and imaginary parts of f of z, in terms of polar coordinates r and theta, and we can use Cauchy Riemann equations in polar form also to check the differentiability of a given complex function. So CR equations in polar form are similar to the CR equations in Cartesian form with some changes. We are writing Cauchy Riemann equations in polar form. Cauchy Riemann equations in Cartesian form are del u by del x equal to del v by del y, and here before writing Cauchy Riemann equations, first we will be given some function f of z. In that function we will use polar form z equal to r into cos theta plus I sin theta of a complex variable. After taking z equal to r into cos theta plus I sin theta in the formula of given function, we will be able to write our function as u as a function of r and theta plus I times v as a function of r and theta. Then Cauchy Riemann equations in polar form can be written in a similar way. Here in Cartesian form we have del u by del x equal to del u by del y. So here also if I am writing the partial derivative with respect to r, here I will write partial derivative with respect to theta. But here with this instead of u we will have v here. If I am writing partial derivative with respect to x of u, here I am writing partial derivative of v with respect to y. Same thing here. Here I am writing partial of u with respect to r, then here I will write partial of v with respect to theta. But here we have 1 divided by r, and we know that we can write polar form for non-zero complex number only. So here z is non-zero, therefore this r, that is length of z or absolute value of z, is greater than 0, therefore this 1 by r is defined. So this is this is analogous to this del u by del x equal to del v by del y. Then second Cauchy Riemann equation in Cartesian coordinate was del u by del y equal to minus del v by del x. So you can imagine here also Now here I am writing partial with respect to theta. So here I will write partial with respect to r. But here we have to multiply with r. Here we are multiplying with 1 by r, and here we are multiplying with r. Otherwise they are analogous to these CR equations in Cartesian form. So remember this Cauchy Riemann equations in polar form: del u by del r equal to 1 by r del v by del theta, and del u by del theta is minus r times del v by del r, and these are defined at non-zero points only. So we can use CR equations in polar form to determine the differentiability of a given complex function at non-zero points only. At z equal to 0, we cannot use these CR equations to determine the differentiability, because here z can be written in this form if z is non-zero, or polar form of a complex variable is defined for non-zero complex numbers only. So if our function is given, then we can use Cauchy Riemann equations to determine the differentiability at non-zero points only. So first requirement is these CR equations are satisfied. Second requirement is all these partial derivatives are continuous at those points where these two CR equations are satisfied. So we take one function and we check its differentiability using Cauchy Riemann equations in polar form. Here I have taken f of z equal to 1 by z, and I am asked to determine whether f dash z exists and its value if it exists. So one more thing, if we have our function differentiable at some point, and if we are using Cartesian form, then derivative was given by f dash z equal to del u by del x plus I times del v by del x. So here also we will have similar formula. Here we will write del u by del r plus I times del v by del r, but here we will multiply with e to the power minus I times theta. That is the difference between these two formulas. Here del u by del x plus I times del v by del x, that is partial derivatives of u and v with respect to x. Here partial derivatives of u and v with respect to r, and this bracket is multiplied with e raised to minus I theta. And if you recall this formula, Euler's formula, e raised to I theta can be written as cos theta plus I sin theta, and if we replace theta by minus theta, then we will have cos theta minus I sin theta. So we will use these formulas also whenever required to simplify our derivative if it exists. E raised to I theta is cosine of theta plus I sin theta, and if we have minus, then we will have minus sign here, and we will use this formula to find out value of derivative at a point where it is differentiable. Now we determine whether f of z equal to 1 by z is differentiable using Cauchy Riemann equations in polar form. Before that, if you wish, you can use complex variable also. You can start with z equal to x plus iy, and you can write your function in u plus iv form. If we take z equal to x plus iy, we will have f of z equal to 1 divided by x plus iy, because f of z is 1 by z here. And to write down this in the form of u plus iv, we have to multiply numerator and denominator by conjugate of x plus iy, which is x minus iy. Then if we simplify this, this is x minus iy. Here we can use the formula of a plus b times a minus b, that is x square minus square of I into y, which is I square y square. Okay, we are using formula of a plus b into a minus b with a equal to x and b equal to I into y. Now we know that I square is minus 1 and we have negative sign here, so this is going to be x square plus y square, and this I can rewrite as x divided by x square plus y square plus I times minus y divided by x square plus y square. And if you compare, this is nothing but u and plus I times v. So here u is x divided by x square plus y square and v will be minus y divided by x square plus y square. Now you can imagine here we will have to determine the first order partial derivatives of this u and v, and then we have to check CR equations. So sometimes if we are using Cartesian form of complex variable, then we have this type of functions, and it is not comfortable to deal with partial derivatives, or it will take more time to find out the partial derivatives of u and v. So in that case we can try for polar form of Cauchy Riemann equations, and using polar form also we can determine the differentiability of a complex function. Now one more thing, here function 1 by z is undefined at z equal to 0. So it is automatically not differentiable at z equal to 0, because z equal to 0 is not in the domain of this function. So we are discussing differentiability at non-zero points only for this function, because at z equal to 0 function is undefined, therefore it is not differentiable at z equal to 0. So these are also undefined at z equal to 0, that is for x and y both 0, but we are not interested at z equal to 0, therefore we can proceed further in Cartesian form also. You can use CR equations in Cartesian form for this u and v, and you can check the differentiability as we have discussed in previous lectures. Here we are going to use polar form of a complex variable, and we will write down our function in that form u plus iv, where u and v will be functions of r and theta. So we start by writing f of z, which is 1 by z, and we can write that clearly f of z equal to 1 by z is not defined at z equal to 0. So therefore we can write that f dash z does not exist at z equal to 0. So we are discussing at non-zero complex variables or non-zero complex numbers only, and we start by considering polar form of z, which is non-zero. Let z equal to r times cos theta plus I sin theta, and this is non-zero. Then we put z in the formula of given function. Our function is 1 divided by z, so we put z equal to r into cos theta plus I sin theta, and we try to simplify this. In the denominator we have cos theta plus I sin theta, and we are taking its conjugate, so we multiply by cos theta minus I sin theta in the numerator and denominator. Here I will write cos theta plus I sin theta multiplied with cos theta minus I sin theta. Then we keep numerator as it is cos theta minus I sin theta. Here r times, here we apply that formula a plus b into a minus b, that is square of cos theta, and negative square of I sin theta, that is I square times sin square theta. Then we can keep this as it is, cos theta minus I sin theta, r as it is, I square is replaced by minus 1 and we have cos square theta plus sin square theta. And finally we are using cos square theta plus sin square theta equal to 1, and we have cos theta minus I sin theta divided by r, and this we can again rewrite as cos theta divided by r plus I times minus sin theta divided by r. Therefore our function is written in this form, u plus I times v, and now we can compare this quantity with u plus iv, and you can see we have u equal to cos theta divided by r and v equal to minus of sin theta divided by r. Now method is simple. First we will determine the first order partial derivatives of u and v with respect to r and theta. Now when we differentiate with respect to r, we consider theta as constant. So cos theta is constant and derivative of 1 by r is minus 1 by r square. Therefore we write this as minus cos theta divided by r square. Then we differentiate with respect to theta. So 1 by r is constant and derivative of cos theta is minus sin theta. So we have minus sin theta divided by r. Same thing here, with respect to r will give me minus sin theta, and derivative of 1 by r is minus 1 by r square. So this is 1 divided by r square into sin theta, or sin theta divided by r square, and del v by del theta is minus 1 by r constant, derivative of sin theta is minus cos theta divided by r. Now we check that CR equations are satisfied or not. First CR equation in polar form is del u by del r equal to 1 by r times v theta. So you can see, if I multiply this v theta by 1 by r on both sides, then I will obtain minus cos theta divided by r square, and that is nothing but del u by del r. So this equation is satisfied at all points z which are non-zero in the complex plane. Second Cauchy Riemann equation is del u by del theta equal to minus r times del v by del r. Del v by del r is 1 by r square sin theta. Suppose I multiply by both sides, by minus r, then you can see here I have minus r and I have 1 by r square into sin theta. So this r will get cancelled and we will have minus sin theta divided by r. So this equation is also satisfied at every non-zero point in the complex plane. So now we can write that clearly, del u by del r equal to 1 by r into v theta, or you can write one more step. We can first write del u by del r, which is minus cos theta divided by r square, and this I can rewrite as 1 by r into minus cos theta divided by r, and you can see minus cos theta divided by r is v theta. Therefore we have 1 by r into v theta. similarly we can write del u by del theta is minus sin theta divided by r, and suppose I multiply this by r, then I have to write in this way, multiply and divide by r. So here I will have minus r square. And what is del v by del r? It is sin theta divided by r square. So if I rewrite in this way, here I have minus r and this is del v by del r. So this equation del u by del theta equal to minus r del v by del r is also satisfied at every non-zero point. So we can write that therefore both Cauchy Riemann equations are satisfied at every non-zero point z, at every non-zero point which we have written in polar form as z equal to r into cos theta plus I sin theta in the complex plane. CR equations are satisfied at every non-zero point in the complex plane. Second condition is continuity of all these partial derivatives. So we can see here z is non-zero, therefore r is positive, and all these functions are continuous functions, because we know that cosine and sine are continuous at every point, and this r square or r, these are polynomial functions, they are also continuous, and in the division we have non-zero quantity, therefore they are obviously continuous at every non-zero point. So that we have to just mention that clearly these partial derivatives del u by del r, del u by del theta, del v by del r and del v by del theta are continuous at every non-zero point, continuous at every non-zero point z in the complex plane. So both the conditions for differentiability are satisfied at every non-zero point, therefore we can say that function is differentiable, or f dash z exists at every non-zero point or at every z not equal to 0, and we have to find its value also. So now we know that f dash z in polar form is given by e raised to minus I times theta into del u by del r plus I times del v by del r. Now we have obtained the values of del u by del r and del v by del r. Del u by del r is minus cos theta divided by r square. So that I am writing here, minus cos theta divided by r square plus I times del v by del r is sin theta divided by r square plus sin theta divided by r square, and as I have discussed, e raised to minus I theta can be rewritten as cos theta minus I sin theta, and you can see here I can take minus 1 by r square common, and in the bracket I will be left with cos theta minus I sin theta, and now I can rewrite this as minus 1 by r square and cos theta minus I sin theta whole square, and then what I am doing is I am multiplying this cos theta minus I sin theta by cos theta plus I sin theta, and therefore for adjustment I have to write cos theta plus I sin theta here and the whole square. After that minus 1 by r square as it is. In the numerator again we can apply that formula, cos theta minus I sin theta. Cos theta plus I sin theta is cos square theta minus square of I sin theta, which is I square sin square theta, and here I have cos theta plus I sin theta as it is and square of this quantity. So what we are writing? We are writing f dash z, and we are adjusting all these terms in such a way that we obtain our answer in terms of z. So now minus 1 by r square as it is, and you can see if I use I square equal to minus 1, I will have cos square theta plus sin square theta, and here I have cos theta plus I sin theta whole square, and then we have minus 1 by r square. Cos square plus sin square is 1 and square of 1 is 1, and we are writing square of this cos theta plus I sin theta whole square. And if you notice, again we can combine these two. This I can rewrite as r times cos theta plus I sin theta and square of this quantity. And if you recall, this is nothing but our z. We started by taking z equal to r into cos theta plus I sin theta. So what we obtain? We find that function is differentiable at every non-zero point, and its derivative at any non-zero point is minus 1 by z square, or we can rewrite this as derivative of 1 by z with respect to z is minus 1 by z square at every non-zero point in the complex plane. And you can observe that this derivative is similar to the derivative for real function 1 by x. We know that derivative of 1 by x is minus 1 by x square, and here also if we have complex variable z, then also derivative of 1 by z is minus 1 by z square. So you can see we can use CR equations in polar form also to find out whether given function is differentiable at a given point, and we can find value of derivative using formula of derivative in polar form. We have used this formula of derivative in polar form to obtain the derivative. F dash z is given by e to the power minus sin theta minus I theta del u by del r plus I times del v by del r, and by making these arrangements or adjustments we are able to derive the formula of 1 by z. So if your function is rational function or this type of functions using quotient or division symbols, then it is better to use CR equations in polar form, which are del u by del r equal to 1 by r into del v by del theta, and del u by del theta equal to minus r times del v by del r. And if function is differentiable, its formula of derivative is e raised to minus I theta equal to del u by del r plus I times del v by del r. And you can do the same problem using Cartesian form of Cauchy Riemann equations also. You can try for this as a homework, and you can see you can compare both the methods, that which one is easy, either easy for Cartesian form of CR equations or for polar form of CR equations. So you can start by differentiating u and v. You can find out first order partial derivatives, and you can check whether these equations are satisfied at every non-zero point or not. So this is all about this session. I hope you like it. Thanks for watching.